All right, so let's do some real stoichiometry now. We just did the mole ratio and hopefully you have that down. If you do not have the mole ratio down, you need to spend some extra time on that and make sure you're understanding that we get that mole ratio from the balanced equation, because we cannot do any stoichiometry without that. Every problem has to go through the mole ratio. This is what's known as the stoichiometry roadmap. I did not give it to you in your notes because a lot of you will not need it. But for those of you that really like a step-by-step process, I suggest that you pause this video and get out a piece of paper and write down this roadmap. Is something you can use. Now, you cannot use it on a test, but as you're getting through these problems and getting familiar with them, then you're more than welcome to use it while you're working the problems. So we're going to start and go through the process, and then if you need to come back, you can always come back and write down this roadmap. All right, so when we're talking about real stoichiometry beyond the mole ratio, I need you to remember, this is where that molar mass comes in. I need you to remember that 1 mole of any substance is equal to the molar mass. So that is how we're going to convert between grams and moles, just like we've been doing quite a bit this year, okay? So again, like anything else, I give you the step-by-step right here, but if we were to like read through each step, it would be kind of confusing, okay? It's better to just kind of show you a problem, and then you can refer back to the steps, okay? But before we start, there's going to be some things we need to know, and that is our conversion factors. Our conversion factors that we're going to need are mole ratio, which every problem needs, okay? We're going to need our molar masses, which we know how to calculate, and then we're going to need this for volumes, because sometimes if we're dealing with gases, you won't have a mass of gas, you will have volumes, okay? And we're going to be using this conversion factor right here, so make sure you're aware of that. 1 mole of any ideal gas is 22.4 liters. You don't know what an ideal gas is yet. You don't know what STP is. We're going to learn that in the gas laws. So for our purposes, we're just going to remember that 22.4 liters is equal to 1 mole, okay, for any gas, okay? Also, remember, we can also do 1 mole is equal to 22.4 liters. So we can use that conversion factor both ways, just like we could for molar mass. So basically, if we're dealing with volumes, instead of molar mass, you're going to use this 22.4 liters per mole. Okay? All right, so let's do a problem and see how we understand it. All right, so first of all, this is going to be a mass to mass, meaning we're going to start with grams and go to grams. Okay? This is going to be very important that you keep track of your units, and this is going to be a big dimensional analysis problem. Okay, so let's read the problem. We want to know how many grams of copper 2 oxide are formed from 6.59 grams of copper 2 hydroxide. For some reason, when the slide printed, it did this little thing here. So we're going to move this over here so we don't have to worry about that over there. So now we've got that in the right place. We look at it, we see, does it need to be balanced? No, it does not. So sometimes we get lucky and everything's 1-to-1, which makes our life easier. So we always start with what we're given. So we're going to start with 6.59 grams of copper 2 hydroxide, which is CuOH2. Okay? Now, remember yesterday we talked about the mole ratio. That's how we get from what we've got to what we want to get to. Okay? But the deal with the mole ratio is you have to be in moles. So we are not in moles, we are in grams. So we have to convert from grams to moles. And the way we do that, molar mass. Okay? And I'm going to tell you we're going to need a pretty long grid. So go ahead and just draw you a pretty long grid. Okay? All right, so I want to get rid of grams of copper hydroxide, so I put it on the bottom. And we already said we were going to use the mole ratio, the molar mass. So we know that it's going to be grams per 1 mole, always per 1 mole. So we have to go add up the molar mass. So copper is going to be 63.55 plus, we have 2 times 16 for oxygen plus 2 times 1.01 for hydrogen, and when we do that, we get a 97.57. Remember, always 2 decimal places. So we'll plug that in, 97.57. And now we got rid of grams. So now that I'm in moles, now I can use my mole ratio. So I want to get rid of moles of copper hydroxide. And I'm going to moles of copper 2 oxide. So now I go to my balanced equation and I see a 1 and a 1, so that makes life easy, so I can put a 1 and a 1. And now I've gotten rid of moles of copper hydroxide. But this is wanting to know how many grams, okay? So I don't know if you've already guessed what that means. That means we need the molar mass of copper oxide. So we have mole of copper oxide and grams of copper oxide. So now we need to get the molar mass of that, okay? Molar mass of copper oxide is going to be 63.55 plus 16, and that is 79.55. All right, now that cancels out. So multiply everything on the top, divide by the bottom. Again, this is when it's your preference of how you want to put it in the calculator. You can do multiply everything on top, hit equal, and then divide by what's on the bottom. Or you can use that N over D key. So when I do that math, I need 3 significant figures, because I have right here 3 significant figures. So when I do that math, I get an answer of 5.37 grams of copper oxide. Now, I encourage you to pause the video and make sure you're calculating this yourself rather than just watch me do it. Okay, I could do stoichiometry problems all day long, but if you're not stopping to do this to see how I'm getting that number, it's going to be difficult. So this is the beauty of the flipped lesson, is you can stop it and pause it and start again. All right, this is another mass to mass. Okay, so we're going to read that. First of all, we have to see, does it need to be balanced? And yes, it does. And so we're going to balance that by placing a 2 in front of NaCl and a 2 in front of HCl. Now that's all taken care of. All right, I'm going to start with my 30 grams of sodium chloride. And then, so 30 grams of sodium chloride. Okay. And then I'm going to divide by the molar mass, because I got to go from grams to moles. Now that I am in grams to moles, I can use my mole ratio, so I want to get rid of moles of sodium chloride, and I'm going to moles of sodium sulfate. Okay, ultimately I'm going to go to grams, but first I have to go to moles. So that's Na2SO4. Now I go look at my balanced equation. I have a 2 there, so I need to put a 2 there. For sodium sulfate, I have nothing there, so it gets to be a 1. So now I cross that out. Okay, now I need mass, because this is how many grams, so I'm going to need the molar mass of sodium sulfate. So I do 1 mole sodium sulfate and grams of sodium sulfate. Okay, again, I calculate the molar mass. This is where I'm going to get this number. It's where I take the sodium, add it up with the sulfur and oxygen mass. And when I do that, I get a molar mass of 142.05. And then I multiply the top, divide by the bottom. I need 3 significant figures, and I get my answer to be 36.5 grams of sodium sulfate, and that is my answer. All right. Let's do 2 more, because we're going to do some volume on there, on some of those, and some other types, so you can see how a volume works. This one wants to know how many liters of oxygen are used to produce 75 grams of SO3. And I'm reminding you to use this for volume. Okay, so first thing we need to do I need to balance it? Yes, I do. And so we're going to put a 2 here and a 2 here. And now it's balanced. Okay, So I'm going to start with my 75 grams of SO3. Okay, when I see grams, I know that immediately I'm going to need a molar mass. So I'm going to do grams of SO3, 1 mole of SO3. So I go find my molar mass of SO3 by adding sulfur plus 3 oxygen, and I get 80.07. Again, I encourage you to stop and pause this. This would be a good time to actually try to set some of it up and see if you do it the way I do it. Okay, grams cancel. Now I'm going to use my mole ratio, so I can go from SO3 to oxygen. So I'm going to have moles of SO3 because I want to get rid of it, and I'm going to oxygen ultimately, so I'm going to do moles of oxygen. So let's go check my balanced equation. I have a 2 here, so I put a 2 in front of SO3. I have nothing there, so I put a 1. Now those cancel out. So now I'm in moles of oxygen. Now we had been going to grams, but this is asking for liters. So we're going to use this conversion right here. And we're going to say for every 1 mole of oxygen, you have 22.4 liters of oxygen. Remember, this is for any gas. It doesn't matter what gas they're talking about. It's all the same. So same concept. I multiply the top and divide by the bottom. I need 3 significant figures for my answer, and so my answer will be 10.5 liters of oxygen. So you see how this little conversion factor here works the same as the molar mass. All right, one more, and then we are done. All right, so first things first, got to balance it. This is a hard one to balance, so I'm just going to give you, oops, go back. Whoops, I went too far on that one, didn't I? Okay, try again. All right, so I'm going to give you this. It's 4, 5, 4, 6. 4, 5, 4, 6. All right, so how many grams of oxygen is used when 85 moles of ammonia reacts? And it tells you what ammonia is, okay? So we are going to start with 85 moles of NH3, okay? Here's the cool thing. If you start out in moles, you don't need to use a molar mass because you started out in moles. You can go straight into that mole ratio. So we're going to go moles of NH3 on the bottom, and we're looking for ultimately oxygen, so we're going to do moles of oxygen on the top. Go to our balanced equation. In front of NH3, we have a 4. In front of oxygen, we have a 5. All right, cancel out moles of NH3. Now, since it wants grams of oxygen, we're going to use, you guessed it, molar mass. 1 mole of oxygen. Now, oxygen is O2, so it's not 16, it's 32 grams of oxygen. Because it is O2 and you have that 2 right there, you got to double it. Again, multiply the top, divide by the bottom. Okay? I need my answer in 2 significant figures. So I am going to round that number, okay, round that number to 3,400. Remember, when I am rounding, I don't just drop off numbers. I got to replace them with zeros. All right? So you have a worksheet on practicing these types of problems. Please be mindful and pay attention to your units, okay? You don't use molar mass if you start with moles. If you start with grams, you need molar mass. If you're doing volume, you need to use the 22.4 liters. Again, you've got those left side activities that have the answers in there. You might want to start with that and check and see if you're doing it right. All right, next lesson will be over limiting reactant. All right.